All right, guys, this is note card 35. This is called Rolle's theorem. And Rolle's theorem is just a special case of the mean value theorem. So before I read it to you, I'm just going to draw a picture which illustrates Rolle's theorem. So as a quick review, all right, let's review the mean value theorem. So what the mean value theorem says, if we have some function, all right, if I call this function f of x, what the mean value theorem says is that as long as this function is continuous and differentiable, that this slope of this secant line between a and b, okay, there's got to be a slope of at least one slope of a tangent line, like maybe right there. Okay, there's got to be some point in between a and b called c, where f prime of c, which would be the slope of this tangent line, equals the slope of the secant line. And the way we'd calculate the slope of the secant line is we would do this average rate of change. Okay. So that's the MVT. All right. Rolle's theorem is a special case of that. Okay. The only difference in Rolle's theorem, the conditions are the same. Okay. So let's call this f of x now. Okay. Conditions are the same. This function has to be continuous and differentiable, which it is in this case. The only difference is, in Rolle's theorem, okay, with Rolle's theorem, the slope of the secant line is 0. So the secant line is completely horizontal. Okay, it's a horizontal line segment. Okay, so here, this slope, okay, because this right here is equal to f of a, but it's also equal to f of b. All right. So if we wanted to do a slope there, we do it exactly in the same way, f of b minus f of a over b minus a. But since f of b is the same as f of a, that just becomes 0 over b minus a, which is 0. So that's how Rolle's theorem is a little special compared to the mean value theorem in general. So if the slope of the secant line is 0, which means that f of a equals f of b, then there's got to be a point somewhere in the interval at c, okay, where the tangent line would also have a slope of 0. So here, this would mean that f prime of c equals 0. Which basically lets me know that on f, I will have a relative max or min. Okay. So if the average rate of change equals 0, somewhere inside this interval, you're going to be getting a tangent line with a slope of 0, which means you would have a relative max or a relative min. Because if I drew the curve the other way, if I drew the curve like this instead, then that would be a relative min. But a relative min also has a slope of 0. So that's the only thing different about Rolle's theorem. It's just a special case of the mean value theorem with one extra condition, that the y values of these 2 points are the same. It's just one extra condition. It's not a big deal. Okay. So let's do some of these examples. It says, determine whether Rolle's theorem can be applied. If so, find the value of c. If not, tell why. So first, let's look at the function. It's got to meet the conditions. Okay, so that's a polynomial. So I can say f is a polynomial. And polynomials are continuous and differentiable. everywhere. Instead of saying everywhere, I can just say on the real numbers. Now we got to make sure the y values come out the same. So let's figure out what f of negative 2 is, and let's figure out what f of positive 2 are, because those are the endpoints. Like there's the a and there's the b. Okay. So when I'm figuring out what f of negative 2 is, I'm figuring out what f of a is. And here I'm figuring out what f of b is. All right, so when I plug negative 2 in, negative 2 to the fourth minus 2 times negative 2 squared. All right, so negative 2 to the fourth is positive 16. Negative 2 squared is 4 times negative 2 is negative 8. So that y value is 8. If I plug in 2 to the fourth minus 2 times 2 squared, well, 2 to the fourth is 16. 2 squared is 4 times negative 2 is negative 8. Okay, so here f of a equals f of b. Okay, so all conditions for Rolle's theorem have been met. So what does that mean? If I subtracted here the slope of the secant line, okay, because these have the same y value, the slope of the secant line would just be 0. Because 8 minus 8, okay, if I would do it here, if I do f of b minus f of a all over b minus a, I would get 8 minus 8 over 2 minus negative 2, that's 0 over 4, which is still 0. So how am I going to figure out where that occurs at? How am I going to find this value of c? Well, let's figure out what the derivative is, f prime of x. From here, that would be 4x to the third minus 4x. Okay. So I have to set that equal to 0. So if I do some factoring here, I can take out a 4x and I get x squared minus 1. If I do some more factoring, I get x minus 1, x plus 1. And then if I use the zero product property, 4 times something could equal 0. That would be 0. Something minus 1 could equal 0. That's positive 1. And something plus 1 could equal 0. So that's negative 1. So I actually have 3 values. And all 3 of these numbers are in this interval. Let me show you what we get here, okay, just graphically so you can understand it a little bit better. So x to the fourth minus 2x squared. I only care about it from negative 2 to 2, and we'll zoom fit. Okay, so there's what the function looks like. So if I connect the secant line between the endpoints, the secant line would have a slope of 0 because their y values are both 8. I'm saying there's 3 places where my tangent line would also have a slope of 0. Right there at negative 1, if we drew in a tangent line, that's a relative min. Okay, so it would have a slope of 0. This point right here is a relative max. So if I drew in a tangent line, it would have a slope of 0. And here at an x value of 1, I get another relative min, so the slope of the tangent line would also be 0. So at those 3 x values, negative 1, 0, and positive 1, my derivative equals 0. And these are the 3 values we just found. So let's read number 2. It says, let f be a function that is differentiable, which we know automatically implies continuous. So the graph is differentiable, means that there's no cusps, no corners, no vertical tangents. All right, and if it's differentiable, it had to be continuous first, so you can draw it without picking up your pencil. So it tells me it's differentiable on the interval 1 to 10. So I'm just going to start kind of plotting some points here. There's an x value of 1, there's an x value of 10. let's see what it tells me. It tells me that f of 2 is -5. So that's a point on the graph of f. It says f of 5 equals 5. Okay. F of 5 equals 5, and f of 9 equals -5. Okay. We're trying to figure out which of the following must be true. Well, if it's continuous, if the graph's continuous, then to get to here, I have to cross the x-axis somewhere in between 2 and 5, at least one time. And this would be known as a 0. I could cross it more than one time. It could kind of come up and then back down and go back up, but it's got to cross at least once. And the same thing here. Since the graph's continuous, to get from that point to that point, I have to cross at least one spot between 5 and 9. Okay, so this is true by the intermediate value theorem. So that one works. One has to be true. Now it says the graph of f has at least one horizontal tangent line. Based on Rolle's theorem, these have the same y values. That means if I draw in a secant line between them, at least one place between 2 and 9, someplace between 2 and 9, maybe it's this point, maybe it's a different point. And maybe the graph kind of does one of these. We have to get at least a horizontal tangent by Rolle's theorem. We got to get at least one horizontal tangent by Rolle's theorem. Okay, so Rolle's theorem makes this absolutely true. And let's read the last one. It says for some c, which means an x value between 2 and 5, the y value is 3. So if you think about this, between 2 and 5, my y values go from -5 up to +5. So another part of the intermediate value theorem says I have to hit every y value between -5 and +5 in between x values of 2 and 5. So am I going to hit 3 somewhere? Yeah, I am going to have to hit 3 somewhere. Okay, so that's absolutely true as well by the intermediate value theorem again. Okay, so they're saying, do I have to hit 3 somewhere for an x value between 2 and 5? Absolutely. So all 3 of these have to be true. All 3 of those have to be true. The reason I told you it had to be differentiable, that's one of the conditions of Rolle's theorem. They're not conditions for the IVT, but it is for Rolle's theorem. So all 3 must be true. All 3 must be true. Okay. So let's look at the next problem. It says determine whether Rolle's theorem is valid for this function. Between the endpoints -1 and 5. So let's just figure out what the y values are. Let's figure out what f of -1 is. Okay. So if I plug in -1, 3 minus the absolute value of -1 minus 2, and that's going to equal 3 minus the absolute value of -3. Okay. And the absolute value of -3 is 3, so the y value there is 0. Let's figure out what it is for 5. 3 minus the absolute value of 5 minus 2. Alright, so that would be 3 minus the absolute value of 3. The absolute value of 3 is 3. Okay, so the y values are the same. So if I was going to make a little graph so far, At an x value of -1, my y value is 0. Okay, and at 5, my y value is 0. Okay, that's one of the conditions met. All right. But what does this graph look like? If I plug in 2 for x, this thing becomes 0 and the y value is 3. But this is an absolute value curve, so you should know what it looks like. It looks like a V. This is actually the high point in the curve. It reaches an apex here at 2, 3. So what do you notice about this function? It is not differentiable. Function is not differentiable because there's a hard corner. Okay. So even though the y values were the same, Rolle's theorem does not apply here. The function is not differentiable at an x value of 2. Why is it not differentiable? Because this graph coming in from the left, it has a slope of +1. Coming in from the right has a slope of -1. Okay, so you could say f prime at 2 coming in from the left does not equal f prime of 2 coming in from the right, because +1 does not equal -1. Okay, let's look at number 2. It says find where the A rock equals the I rock. So this is an example of mean value theorem. So for this to hold, what do you know? All right, so that means y needs to be continuous and y needs to be differentiable. So if you remember what that curve looks like, okay, a regular square root curve looks like that. And if it's an x minus 2 in the parentheses, all that does is shifts it 2 units to the right. So if I plug 2 in here, I get 2 minus 2 is 0 and the square root is 0. And if I plug in 6, 3, 4, 5, 6, 6 minus 2 is 4 and the square root of 4 is 2. So looking at this curve, is it continuous? Yes. Is it differentiable? Does it have any cusps, hard corners, or vertical tangents? No, it doesn't. So it is continuous and it is differentiable. So let's figure out the A rock first, okay, between 2 and 6. Okay. We would do f of 6 minus f of 2 all over 6 minus 2. Well, what is f of 6? It's 2. What's f of 2? It's 0. All right, 2 minus 0 is 2. 6 minus 2 is 4. So the slope of the secant line here is a half. Okay, because I'm rising 2 and I'm running 4. Now, let's figure out the equation of the derivative. So here, y equals x minus 2, the square root of all that, which I can write as 1/2. All right, so I got to take the derivative of that. So the 1/2 comes down. This is a chain rule. We reduce the power by 1. All right, and then you multiply times the derivative of the inside. Okay, just a chain rule. So if I'm going to rewrite this, this becomes 1 over 2 times the square root of x minus 2. So what do you have to do to figure out what value of x, okay, somewhere in between an x value of 2 and an x value of 6, if I draw on the tangent line, it should also have a slope of a half. My goal is to figure out what x value that happens at. Okay. So let's set that equal to this 1/2. Okay. So whenever you have a proportion, we cross multiply. 1 times 2 is 2. 1 times all of that in the denominator still equals that in the denominator. How would you solve this? Well, the first thing I would do is I would divide both sides by 2. 2 divided by 2 is 1, so 1 equals the square root of x minus 2. Okay. To get rid of the square root, square both sides. So 1 squared is 1. Square roots cancel squares, x minus 2. Okay. Add 2 to both sides, so x equals 3. Okay. At this x value of 3 right there, the slope also equals a half. If I plugged in 3 right here, 3 minus 2 is 1, square root of 1 is 1, 2 times 1 is 2, 1 over 2 is 1 half. All right, number 3 should be a review question for you. Critical numbers. What do we know about critical numbers? It's where y prime equals 0 or y prime is undefined. So we have an equation for y. So y equals the square root of x squared minus 2x minus 15, but I'm going to write that as to the 1/2 power. So just like before, use the chain rule, bring the 1/2 down, keep the parenthesis the same, reduce the power by 1. Now multiply that times the derivative of the inside. Here's the inside. So the derivative of that thing would be 2x minus 2. Which is really like 2x minus 2 over 1. So y prime equals 1/2. Let's rewrite the second term as x squared minus 2x minus 15 to the positive 1/2, or as a square root like that, times, if I wanted to do some factoring, I could take a 2 out of both of these terms and I would be left with x minus 1. All right, so what happens if you multiply all those? Well, this 2 can cancel that 2. So you're left with a derivative of x minus 1 over the square root of x squared minus 2x minus 15. So here's the derivative. How am I going to figure out where it equals 0? It's where the numerator equals 0. Because if the numerator is 0, the whole fraction is 0. What number minus 1 would give me 0? X equals 1 is a critical value. If it's defined for the function. Okay. So if I actually plug it back in, that would be the square root. 1 squared is 1, 2 times 1 is 2, minus 15. So y sub 1 equals the square root of negative 16. Well, we know we can't take square roots of negative numbers in the real number system. So 1 doesn't actually exist on this graph, therefore it can't be a critical number. It has to exist on the graph. All right. Now, where is the derivative going to be undefined? It's going to be undefined if the denominator equals 0. So let's take the denominator and let's set that equal to 0. Square both sides, square root goes away, 0 squared is still 0. Do some factoring, x minus 5 times x plus 3 equals 0, and get 2 answers here. All right. So, when I do that, I get 5 and negative 3. Well, what would happen if I put 5 or negative 3 in here? We just figured out, for those two numbers, you should get out 0. 5 squared is 25, 2 times 5 is 10. 25 minus 10 minus 15, that's 0. Okay, that works out. Negative 3 squared, that's 9. Negative 2 times negative 3 is positive 6. 9 plus 6 is 15, minus 15 is 0. Square root of 0 is 0. Okay. So these are the 2 critical numbers. Graphically, let's look at it. Let's look at that function. Square root of x squared minus 2x minus 15. Okay, let's just do zoom standard. So here's what the function looks like. Okay, there you go. Hopefully you can see right here at this point you would get a tangent line that's vertical, which means that the derivative's undefined, because you get a vertical tangent line there at -3, and you would also get a vertical tangent line here at +5. Notice, okay, I thought one of the answers was +1 from the calculus, but 1's not defined on the graph. All right. Number 4, another review question for us here. We want to locate the absolute extrema, which means we want to find the absolute max and the absolute min. What do you know about absolute extrema? They happen at endpoints or at critical values. They happen at endpoints or at critical values. Now 1 here is an open. Okay, 1 is open. All right, so we're not actually going to include 1. All right, one of the conditions of extreme value theorem is not met. We might not get a maximum. Okay, but let's say it wasn't an open interval. Let's say it was closed. So I'm just going to put 1 with a circle around it so I know when I plug 1 in, that's not a real point on the graph. Okay, so if I plug 1 in, 3 over 1 minus 1, I can't get it. It's undefined. There's a vertical asymptote there. Okay, if you get really close to 1, like 1.01, all right, so what's going to happen here, the graph of this, if I think about it, at 1, there's a vertical asymptote. So the graph actually does one of these. The graph does one of those. And if I plug in 4, here, 4 minus 1 is 3, 3 over 3 is 1. So this is the 0.41. Okay, so just by knowing what the graph looks like, I know right away that I'm only going to get an absolute minimum of 1 if you know what the graph looks like. Now let's say you didn't know that. Okay, so we figured out what the endpoint value is. Let's figure out if there's any critical values. So let me rewrite f of x here as 3 times x minus 1 to the -1 power. So to find critical values, you got to take the derivative. All right. So you do 3 times the -1, that's -3. We're going to reduce that power by 1. And you're going to multiply times the inside, the derivative of the inside, which is just 1. So f prime of x here would equal -3 over x minus 1 squared. Well, how do I figure out where there's critical values? Set the numerator equal to 0. Is that ever true? Nope, -3 never equals 0, so there's no critical values from there. All right. And what about setting the denominator equal to 0? What number minus 1, then square it would give me 0? Well, only if this parenthesis was 0. The way this parenthesis gets 0, x equals 1 is a critical value. But 1 is not defined on this function, okay, because there's a vertical asymptote there. So we can ignore this critical value. So there's actually no critical values. So this function has an absolute minimum, but it has no absolute maximum. Okay. As this goes closer and closer and closer to 1, this goes up towards infinity. So there's no absolute max. All right. Going to the next question. Determine if Rolle's theorem applies to this function for -1 to 3. If so, find c. If not, tell why. So that's a polynomial. this whole thing's a polynomial. So if you multiply, so I know that this thing, a polynomial, is continuous and differentiable. If you multiply two polynomials, they're also going to be continuous and differentiable. So I know right away f of x is continuous and differentiable. So the first two conditions are met. Now, do they give us the same y value? What's f of negative 1? So I would do negative 1 minus 3 times negative 1 plus 1 squared. Hopefully right away you can see that this becomes 0. 0 squared is 0, and anything times 0 is still going to be 0. Now what about that endpoint? 3 minus 3 times 3 plus 1 squared. 3 minus 3 is 0, times anything is still going to be 0. So the y values are the same. So it meets all conditions. Okay. So Rolle's theorem is going to apply. Rolle's theorem is going to apply. So I know right away that the slope of the secant line, or the average rate of change between negative 1 and 3, is going to be 0. Now I got to figure out where is the slope of the tangent line, which we call f prime. So where is f prime equal to 0? So let's figure out what f prime is. Okay, so f prime of x, if I notice here, to me this looks like a product, so I could use product rule. Okay, so the derivative of the first parenthesis, so the derivative of just x minus 3 would be 1 times the second parenthesis, which is x plus 1 squared. Product rule always a plus. Okay. Plus the first term, x minus 3, times the derivative of this second term. So I have to use chain rule here. The 2 comes in front. The parenthesis stays the same. We're going to reduce the power by 1. And we're going to multiply times the derivative of the inside. In that case, it's just that. So if I do some simplifying here, I get 1 times x plus 1 squared plus, well, 2 times 1 is 2 times an x plus 1 to the first, okay, times an x minus 3. So if I want to do some factoring, both terms have an x plus 1. So I can factor out an x plus 1. Well, I took care of one of these x plus 1, so I need to add in another x plus 1 there. All right. Here I have the x plus 1 already taken out, but I still have a 2 times an x minus 3. So I could actually distribute that. So if I distribute that, it would just be 2x minus 6. So this becomes x plus 1, and inside that big bracket, x plus 2x would be 3x, and positive 1 and a minus 6 would be negative 5. Okay. So that's what the derivative function is. We've got to set it equal to 0. We've got to set it equal to 0. So what values of x from those parentheses would turn that into 0? Well, hopefully you say right away, well, negative 1 would. And then here, if you set this thing right here equal to 0, you add 5 and then divide by 3. So x would equal 5/3, or 1.6 repeating. Now, are both of those valid answers for Rolle's theorem? Remember, it says it has to be continuous on the closed interval negative 1 to 3, but differentiable on the open interval negative 1 to 3. So if one of the answers is an endpoint, we actually exclude it. Okay? We want to find the number in between. Okay? We want to find the c's that are in between negative 1 and 3, not including. Okay? So we're going to get rid of the negative 1 answer. So the only answer that's right here is 5/3. 5/3 is the only value. Number 6 is a little bit tricky here. It says, suppose that f of 0 equals 4. So if I'm looking at a graph, when the x value is 0, the y value is 4. All right. And here it says that the derivative is less than 2 for positive x values. Okay. It says apply the MVT to the interval 0 to 3 to prove that f of 3 is less than or equal to 10. Okay. All right, so we have to make an assumption here. We have to assume f is continuous and differentiable. It's continuous on the closed interval 0 to 3 and differentiable on the open interval 0 to 3. Okay. So what does the MVT say? I want to end up saying this. I want to say f of 3 equals, or f of 3 is less than 10. So MVT says that the A rock has to equal the I rock. So the A rock between 0 and 3 has to equal the I rock. Okay. So the A rock, how would I calculate the A rock? I would have to say that f of 3 minus f of 0 all over 3 minus 0. That's how I would do the A rock. All right. And the I rock, okay, is f prime at some number c, where c is some number in between 0 and 3. Okay. So I can start to plug in some numbers they give me. I don't know what f of 3 is yet. Okay. But I do know that f of 0 is 4. Okay, so I can say that. All right. And I know that the derivative is always less than or equal to 2. All right. That's going to be less than or equal. So this number is less than or equal to 2. Now, why did I put a greater than? This is going to be greater than or equal to 2 because the derivative is less than or equal to 2. So if we kind of do a little math magic here, 3 minus 0 is 3. Oh, I'm sorry, this should have still been less than or equal to. Sorry about that. Because I know these things have to be the same, so if it says this has to be less than or equal to, then this would also be less than or equal to 2. Sorry about that, just didn't think through it enough. So what can I do here on both sides with this inequality? I could multiply both sides by 3. That would get those to cancel. Okay. So now I get f of 3 minus 4 has to be less than or equal to 6. Right, and then and it's going to stay the same way because I'm multiplying by a positive number. When you add or subtract, the inequality does not switch signs. So f of 3 has to be less than or equal to 10, which is what they wanted me to prove. Okay. So therefore it has been proved. All right. So what they're saying here, if that's an x value of 3, and this is 10 up here, all right, that's got to be 10 or less because the slope of this thing and the slope of the secant line has to be 2 or less. So the slope of this is 2 because you're going up 6 and over 3. But it could be smaller than that. So it could be something like here, okay, or it could be a less steep slope. So how would those be possible? It would only be possible if the y value is 10 or smaller. So that's graphically what we're doing. If we want the slope to be 2 or less, or to be the steepness of 2 or less, the y value has to be 10 or less. And I use the definition of the mean value theorem to prove how it's true. All right, so that's going to seal it for this note card on this packet right here. It's just a lot of good review problems from the last few note cards. Okay, so there is note card references if you have to go back and look at it. Okay, so here is like derivatives of inverse functions. Okay, here's derivatives of exponentials. If you want a quick review on here, the a value is 3, so y prime would be ln of 3 times the whole function itself again times the derivative of just the exponent. Okay, so there's a freebie for you. Find the IROC, or the derivative at x equals 1 for this quotient function. Determine if Rolle's theorem applies. Okay. Here's a mean value theorem problem. Okay. Absolute extrema. It's finding a derivative of a product. Finding critical numbers. So a good review sheet. So try to get that done this evening.